Hi, my name's Phil, this is Apollo, and today but mostly I, will be talking to you about angular momentum. Now, we'll start off with something a little simpler than angular momentum. In physics, one of the most useful concepts is that of conserved quantities. These are things that don't change their total amount over time. And by knowing how much of a thing there was before an event or after an event, we can use the fact that there must be the same amount before and after to understand what happened. Now, as an example, mass is a conserved quantity. So if I take an apple and I chop it in half, I still have the same total amount of apple, even though it's now in separate pieces. So how much did the apple weigh originally? Well, all I need to do is weigh these two separate pieces and use the fact that mass is conserved. Now, this might seem like a trivial thing to say. Of course, if I chop an apple in half, I don't get any more or less apple. But this concept is of fundamental importance. The idea of conserved quantities is very simple, even though with things like angular momentum, the things themselves that are conserved are not always simple. So I've talked about mass so far because it's highly intuitive. We understand what it means for one object to be heavier or lighter than another. When I was first taught about angular momentum, however, I found it anything but intuitive. But it's really important for understanding all sorts of things because it's a conserved quantity. So my aim in this video is not to give you a mathematical definition of angular momentum, but rather to try and give you some intuition for it. Angular momentum is most often associated, and it's easiest to understand, with objects that are spinning or orbiting around something else. The Earth, for example, has angular momentum due to its orbit around the Sun. The solar system, in turn, has angular momentum as it orbits the centre of our galaxy. Now, closer to home, we can try to get a feel for this by spinning a mass on a string. So here I've got an avocado stone that I've drilled a hole in and threaded a piece of string through. And this is something you can easily try yourself at home as well. Now let's see if we can develop some intuition for angular momentum. So if we start by only having a short length of string between my hand and the avocado seed, I can spin it round, but it needs to move quickly in order to keep orbiting my hand. If I slow down, the seed is no longer supported by the spinning. If I now have a longer piece of string between the seed and my fingers, I find that I can spin the seed much more slowly without it falling. So somehow, the angular momentum of the seed depends on how far away it is from my hand and how quickly it's moving. And when one increases, the other can decrease. So it turns out, in fact, that the seed spinning on a piece of string is more complicated than a planet orbiting a star. Of course, planets aren't connected to their stars by strings, and the seed felt the additional force of the Earth's gravity. But there's another experiment we can do where we can actually feel for ourselves these effects that we've just seen. So I'm going to go into another room now where I've got a bit more space, sit on a chair that I can spin round on, and when I do, I will have some angular momentum. Now, when I extend my arms and legs, you can hopefully tell watching this video, and I can certainly feel that I slow down. But what's really weird is when I tuck my arms and legs back in, I speed up. Now, this is a lot of fun and definitely something you can try yourself at home. Eventually, of course, my chair stopped spinning, no matter what I did with my arms and legs. So does this mean that angular momentum wasn't conserved? Well, no, we just need to think about the bigger picture. The chair wasn't spinning in isolation. I was interacting with the air and it was connected to the floor. Although I no longer have the angular momentum, this is because it was transferred to the air around me and also to the Earth itself. The idea of angular momentum conservation and of transferring angular momentum from one thing to another is extremely important in astrophysics. In my work, I use supercomputer simulations to study the supermassive black holes at the centre of galaxies and how they affect galaxy evolution. Gas orbits these black holes, just like the Earth orbits the Sun, and despite the immense gravity of the black hole, the orbiting gas still has to lose angular momentum in order to fall into it. This is also the case when two black holes orbit one another. In order to actually collide and merge, they need to somehow lose their angular momentum. And one way to do this is by emitting gravitational waves, which we can then detect with experiments like LIGO. But for supermassive black holes, this isn't an efficient way to do it. and in fact there's a long-standing problem in this field known as the final parsec problem. The main way for orbiting supermassive black holes to lose angular momentum is by slingshotting gas clouds and stars away from them. Angular momentum is transferred to the gas and stars, and the black holes can then move closer together. Eventually though, when the black holes are close enough, there are no more nearby stars and gas clouds to transfer angular momentum to. Now we think that supermassive black holes do merge in the universe, and so trying to understand and solve this problem is an area of active research. Hopefully in this video I've given you some basic intuition about angular momentum, as well as an idea for its place in modern astrophysics. If you have any questions, feel free to leave them in the comments below, and thanks very much for watching.
Astro 3D is the Australian Research Council's Centre of Excellence for all-sky astrophysics in 3 dimensions. Our astronomers are searching to understand the evolution of the matter, light and elements from the Big Bang to the present day. This Astro in the Home series is your opportunity to unlock the secrets of the universe with your own 2 hands. Find out more by visiting our website, following us on social media, or subscribing to our YouTube channel to be notified whenever we upload new content. Now, go explore the universe.